Sathyabama Institute of Science and Technology.
Hi dynamic learners, wish you a great day from Dr. A. Viji Amutha Mary, Professor, Department of Computer Science and Engineering, Sathyabama Institute of Science and Technology. In this video lecture, we are going to discuss another interesting topic, that is Huffman coding. Huffman coding is a lossless data compression algorithm. It is used to compress many types of data such as text, image, video, audio, etc. It's usually used in image and video compression. So here the Huffman coding is implemented using a greedy approach. As we all know, greedy algorithms are a class of algorithms that make optimum decision at each step with the aim of finding a global optimum solution. Examples of such popular greedy algorithms are Fractional Knapsack, Dijkstra's algorithm, Kruskal's algorithm, Huffman coding and Prim's algorithm. So now we are going to discuss the Huffman coding technique. So Huffman coding is a data compression algorithm. The idea is to assign the variable length codes to input characters, and the lengths of the assigned codes are based on the frequencies of the corresponding characters. So the variable length codes assigned to the input characters are prefix codes, meaning the codes are assigned in such a way that the code assigned to one character is not the prefix of code assigned to another character. Thus, it makes sure that there is no ambiguity when decoding the generated bit stream. There are two major parts in Huffman coding technique. The first one is building a Huffman tree from the given input characters. And the next step is traverse the Huffman tree to assign the codes to the characters. So these are the two major parts in Huffman coding technique. Now let us discuss the steps required to build the Huffman tree. So given a set of input characters, now we have to create a leaf node for each unique character and build a min heap of all the leaf nodes. Then the next step is extract two nodes with the minimum frequency from the min heap. The next step is to create a new internal node with a frequency equal to the sum of the two nodes' frequencies. So make the first extracted node as its left child and the other extracted node as its right child. Now the steps 2 and 3 are repeated until the heap contains only one node. The remaining node is the root node and the tree is complete now. Let us see the explanation with an example. Here are the input characters and the corresponding frequencies. For A, the frequency is 5. That is, the number of occurrence of character A is 5. And for B, the frequency is 9. C, it is 12. And for D, it is 13. For E, it is 16. And for F, it is 45. So the next step is you have to build a min heap that contains 6 nodes because the input set is 6. So each node represents a root of a tree. So we are building a min heap with each node representing the root of the tree. Now extract the two minimum frequency nodes from the given heap. So the two minimum frequencies are 5 and 9. Extract those nodes, okay, form a node structure and find the sum of 5 and 9. Okay, the resultant sum is 14 and that is the internal node here. So an internal node is created by adding the sum of the frequencies of the two minimum frequency nodes. So we have got the internal node like this. So now the updated min heap contains 5 nodes where 4 nodes are roots of trees with single element each and one heap node is root of tree with 3 elements. Now the updated table is given here. So C, D are the characters, their corresponding frequencies are given here. And the next one is the internal node which we have created in the last step and its frequency is 14. The next nodes are E and F, their frequencies are 16 and 45. Like this we have updated the table now. Now what will be the next step? Now find the next two minimum frequencies. That is, the next two minimum frequencies are 12 and 13. So create an internal node out of these frequencies. So extract the next two minimum frequency nodes from the heap, add a new internal node with the frequency equal to 12 plus 13, which is equal to 25. So now we have created another internal node which is equal to 25. So now the updated min heap contains 4 nodes now, where 2 nodes are single nodes and the other 2 nodes are the internal nodes. So the frequency is also updated in the increasing order. Okay, so internal node contains the frequency 14 and E is of frequency 16, internal node 25 and F is of frequency 45. So again, extract the two minimum frequency nodes. Add a new internal node with frequency equal to 14 plus 16, which is equal to 30. So here we have created a new internal node, that is 30. Okay, now let's go to the next step. Now the updated min heap contains only 3 nodes. So the 2 are the internal nodes and 1 is the single node F. Okay, so now what are the minimum frequencies here? 25 and 30 are the minimum frequencies. Now create an internal node out of 25 and 30. So extract the two minimum frequency nodes, add a new internal node with frequency 25 plus 30, which is equal to 55. So now you can see the tree structure. So 55 is the root node and you can see that the lesser node always go to the left subtree. See, when you compare 25 and 30, the lesser node is 25. So it is always placed as the left subtree. And the greater node, that is 30 is greater than 25, that is placed as the right subtree. So in the next step, again the min heap is updated and it contains only 2 nodes. One is the single node F, whose frequency is 45, and the next is the internal node, the frequency of which is 55. Now extract the minimum frequency nodes and add a new internal node with frequency 45 plus 55, which is equal to 100. So 45 and 55, the sum of these frequencies are added. From the sum of these frequencies, a new node is created. That is 100. The frequency is 100. Okay, so now also you can see that the left node of 100 is 45 and the right node of 100 is 55. So when you are comparing the values 45 and 55, the lesser node is 45. It is always placed as the left subtree. And the greater node is 55, which will be placed as the right subtree. So now the min heap contains only one node and here we are terminating the algorithm. So now we have built the tree, Huffman tree, from the given set of input characters. Now the next step is assigning the codes to the characters. For assigning the codes to the characters in the Huffman tree, first traverse the tree starting from the root node. Maintain an auxiliary array. So when you move to the left node, when you move to the left subtree, you write 0 to the array. When you move to the right child, you just write 1 to the array and print the array when a leaf node is encountered. So starting from the root node till the leaf node, when you are moving to the left array, you just assign the code 0, and when you are moving to the right array, you just assign the code 1. Here we have assigned the codes. So starting from the root node from 100 to 45, since it is a left node, we have assigned the value 0. When you are encountering a right node, you just assign the code value 1. So in all the subtrees, okay, you do the same assigning process. When you encounter a left node, just assign 0. When you encounter a right node, just assign 1. So now we have come up with the code words for the given characters. For example, for the character F, so here is the character F, the code word is 0. So starting from the root node, you just traverse the path till the leaf node. So the values along the path will be the code words. Okay. So now let us see another character, that is C. So for C, the values are, so starting from the root node, you just traverse till that node. So 100 is the code word for C. So likewise, we have assigned the code words for each and every input character, and we find that the minimum code word will always be nearer to the root node and the lengthier code words will be nearer to the leaf node. So thus we have assigned the code words to the characters. The Huffman codes are assigned to the given characters. We are going to discuss the interesting part, that is the analysis part. What is the time complexity and space complexity of Huffman coding? Here the extract minimum, actually at each step we find the minimum frequency nodes from the given characters. So for extracting that minimum nodes, it takes log n time. So if there are n nodes, the time is given by n log n. Okay, so the overall time complexity of Huffman coding is big O of n log n. And the space complexity is a linear one, which is denoted as big O of n. And Huffman coding is used in a variety of applications, like it is used for transmitting facts and text, it is used for video and image compression, it is used by conventional compression formats like pkzip, gzip, etc. It is useful in cases when there is a series of frequently occurring characters. We have come up to the end of the session. Thank you learners for listening to this video very patiently. We'll meet you again in the next video lecture. Thank you all.